Okay, are there any questions on your assignment? It was easy? Relatively easy? No? MATLAB?
It takes some time.
Takes some time, yeah, yeah. Okay, I am preparing the next one. So once I finish these maybe 6 or 7 lectures on methods for introducing various problems, I will be able to give you an assignment as an experience on each class of problems. And then we'll move on to developing models and then to numerical methods. So in the last lecture, we just looked at the flash problem, how to solve it in COMSOL, how to solve it in MATLAB. And then we started looking at the continuously stirred tank reactor problem as an example of a system of nonlinear algebraic equations, 2 equations in 2 unknowns. And I want to continue with that because this is a problem, as I said in the last class, that's rich in terms of the behavior that it exhibits. So we'll come back to this problem later on, in fact, to look at stability issues, etc. But the problem is a fairly simple one. You have a stirred tank reactor into which you feed a certain chemical and it reacts to produce a certain product. You know, the feed rate, the temperature, and the composition are related by the mass balance and the energy balance. So these are the 2 equations that you see here. Oops. The mass balance, and this is the energy balance. And there are 2 unknowns, Ca and T, the concentration and the temperature. But there are a number of parameters. There are about 15 parameters in there, including the feed rate, the coolant rate, the heat of reaction, etc., the properties. And the values are all given to you in the table here. And these are 2 nonlinear equations. They are treated as algebraic equations when you have steady state solution. That is, when you set the left-hand side is equal to 0, it reaches a steady state. And the solution to that is obtained by solving a problem of this type, f of x, p equal to 0. So x in this case is, as we saw, a vector containing 2 elements, Ca and temperature, and p is a set of 15 numbers that are given in the table, and the 2 equations, f1 and f2. We need to make these 2 equations equal to 0. So if I ask you the question, how many such solutions are possible, that is values of Ca and T that will satisfy these 2 functions equal to 0, the answer is nobody knows. The mathematicians don't have any theory to tell you beforehand how many such solutions are possible. Okay, so that's where the challenge is, and the nature hides its secrets from us in the form of a nonlinear equation. If I give you a linear equation, you know that there is a unique solution, right? There is only one solution, and you know how to find it, and you have seen that in the backslash operator in MATLAB. But for nonlinear problem, that's not the case. Now, in the last lecture, we solved this for one set of parameters, starting with some initial guess. FSOL requires a guess that you have to give. Starting with that guess, we saw how the communication goes back and forth between FSOL and the function that we wrote to find that solution that satisfies those 2 sets of equations. And I want to pick up from that where we left off and talk about these other issues of what are multiple solutions. When you have multiple solutions, how do you reach any one of those many different solutions? The simplest example, let me give you. If the function is, let me go back here. If the function f of x is given by this, sine of n by x equal to 0. And then I ask you, how many such solutions are there? How many values of x will satisfy that equation? There are infinitely many. That's easy to know because I know how the sine function looks, right? Whenever it crosses the x-axis, that is a solution. right? So this is an example where we know a priori that there are infinitely many solutions. But a nonlinear equation like this, there is really no theory that tells you beforehand that there are 2 solutions or 3 solutions or 4 solutions. So we need to find these solutions by using very sophisticated numerical methods, and MATLAB doesn't have it. COMSOL has a little bit more sophisticated tools to find such multiple solutions. But let's try to solve this using MATLAB and see what we get. Okay? So this is what we saw in the last class. We wrote a MATLAB script, and there were 15 parameters. They were given in the table. We input them, and then we stopped exactly here after solving part A. So x0 equals 0.2 and 380 are the 2 guesses for the concentration and temperature, initial guesses. And then we set for the solver certain parameters like the tolerance. We want the function to be less than 10 to the minus 7, and display off, meaning don't print off after every iteration. But the real tool in MATLAB that you need to understand is this fsolve. Okay? fsolve solves any system of nonlinear algebraic equations. You need to identify what the problem is. So you need to write a function, in this case CSTRFN, that programs those 2 equations. Okay? And then that function in this case is taking a vector x, that vector is of length 2, contains concentration and temperature, and a set of 15 parameters that we have defined in lines 1 through 19. And then it takes a set of initial guesses, x0, which is given here in line 21, and then the options parameter that is defined in line 22. So the control goes to fsolve, fsolve solves the problem, gives back our solution, and I store it in a vector called xs. xs will also be of length 2. The first element will be concentration, second element will be temperature. So let me just set a breakpoint here and then run this to see what we got as a solution. Okay? So fsolve solved those 2 equations and gave me for concentration 0.2645 and for temperature 393. Okay? And I can verify that these are indeed the true solutions by calculating CSTRFN, XS, comma par. Okay? So I'm calling directly that function to see how do those functions evaluate. They should evaluate to 0. Okay? And they evaluate to 10 to the minus 12. So that is the true solution. The question is that the only solution? Okay? And the answer to that is no, there are other solutions depending on the parameters. Okay? And this is why this was worth a PhD thesis in the 50s, as I said in the last class. It's a fairly complicated problem. For the first time, someone studying that, it's going to be pretty challenging to get these solutions. Now, before we do that, I pose the second problem, and the problem is I want to now look at the solution. How does the solution change as one of the control parameters changes? The flow rate in this case. The flow rate changes from 1 to 30 in steps of 1. I want to generate solutions for flow rate of 1, 2, 3, 4, etc., all the way up to 30, and maybe plot them. Okay? Here I'm just printing them out. So that's fairly easy to do. All I need to do is set up a loop for the flow rate, and f is the variable that represents the flow rate, but I need to put it into the parameter set, because the way I'm passing the flow rate is through this parameter set. So par 1 contains the flow rate. If we go through the list here, par 1 contains the flow rate, f. Okay? So I take that loop counter f, which has the value of the flow rate, and put it into par 1, and options is the same as before, and I call fsolve in the same way as before, and with the same initial guess, x0, that I have before. Okay? And every time it goes through this loop, PAR at one location will have different values. Flow rate of 1, flow rate of 2, flow rate of 3, etc. Okay? And when it comes out in line 30, it's going to return the converged solution, if it converges. Okay? And I'm just printing those solutions, including the flow rate now, and the concentration and temperature. So if I run this, what you will find is, so it is printed for the very first value. Okay, steady state solution for F. Flow rate is 1, Ca is 0.2645, and temperature is 393. Okay, and that was the original solution we had because we had Fa as equal to 1. Okay, but now when I step through this, you will find that it goes through. Now here I'm doing something. What am I doing? Can you guess? What is the implication of that line 32?
So the initial guess to
The next time around when it solves for F equal to 2, I don't want to use the same x0. I wanted to use the most recent solution that it found as the guess. But I'm going to change the flow rate to 2. Okay?
So we're basically using the flow rate of the previous solution. I mean, the solution
Converts.
flow rate and use it for the next.
Right. So if I have a converged result for F equal to 1 and I want a solution for F equal to 2, I'm taking the previously converged result and giving it as an initial guess. Okay. So if you want to imagine this, the graph of what I want to plot is going to be, if I can get the, yeah. So what I want to generate is F as a function of Ca or F as a function of T. Okay. So here I have one point at F equal to 1. And the next point may be like this, the next point may be like that, right? But I'm going to say use this as the initial guess and then converge to that. Okay, and then use that as the initial guess and converge to that. Okay, I could have used this itself as the whatever I was giving as the initial guess for every one of them. Then what would happen? It'll have to work harder, right? Because the initial guess is getting poorer and poorer as you go farther away. And sometimes it may not even converge. We can actually try that as well.
So,
yeah.
This is only valid for such a case. Like if you have suppose a parabolic concentration profile, then maybe this is not actually be viable way to like the initial guess would be the correct one. They could converge to the previous value.
Once you change the F value from 1 to 2, the solution changes. We don't know whether the solution above or below. And we don't know how far above or how far below. Right? So that is an uncertainty because we don't know where the solution is. So all we are saying is if you know something better, you can use an initial guess closer to that. Not knowing anything better, this is my best guess. Okay? And we will see later on that you can actually do a better job of coming up with better initial guess. And that will speed up your convergence. So you can construct a whole solution using something called continuation method that is built into COMSOL, but not in MATLAB. You need to implement that in MATLAB by ourselves. And we will see that later on. But right now, yeah, we don't know exactly what is the best initial guess, but this is the best we can do. Okay? And if you make small changes in F, you are hoping that the solution will also change by a small amount. That's a big if. Okay, and that's one of the things that we are going to see is not true. Okay, so let me then continue one more time. So right now, F is already 3. I've gone through the loop 3 times. Right, one more time, etc. And each time it prints out what the flow rate is, and you can see that the composition is actually decreasing, and it's decreasing significantly, and the temperature is increasing. Okay, and maybe I will set up the breakpoint and take that out and continue. Where am I now? It's still 6, so let me set the breakpoint there and take that out. So now I've gone through the 30 times, right? So I have the data, but I have not saved any one of them. I've just kept overwriting on that. So I don't have ability to plot that result. Okay, so if you want to plot the result, you know the trick, right? You need to accumulate the vector using either the counter or appending to the previous length of the vector. But what you see from here is a fairly gradual change in flow rate and composition. 0.26, 0.16, 10, 07, 05, 04, etc. Fairly smooth. So it looks like that the curve is smooth means that there is possibly only one solution. Okay. The next thing I'm going to do, any questions on this? I'm progressively showing how to set up the problem for more and more complicated situations. And we'll go and do the same thing in COMSOL. Okay? So the next stage is I'm going to illustrate that for some values of the parameter, there are actually 3 solutions. Okay? So in this case, parameter 1 is the flow rate. I fix it at 1. Parameter 4 is 343 degrees. Now, parameter 4 is the T0. Okay, so that's an inlet temperature, right? And parameter 10 is 310, and parameter 10 is a cooling water temperature. Inlet temperature, cooling water temperature, and parameter 14 is one of the coefficients in the correlation for heat transfer. Okay, so if you go back and see the A and B, these are parameters that are appearing in this expression, which is essentially a heat transfer coefficient as a function of flow rate multiplied by the temperature gradient. Okay, that's A. What was the other one I changed?
B.
B. Where is B?
It's the
Temperature.
No, it's
The power, right? The exponent of the flow rate. Okay, so that is, can you kind of relate it from your undergraduate fluid mechanics, what that exponent and A are? It's like a Reynolds number, right? Reynolds number to the power 0.8, for example, in turbulent flow. You'll find that. So it comes from there. Okay, so B is 0.5. So if I change the parameters to a different set as I've given here, and this is the crux of the thesis work, because they need to search the parameters to see where the reactor behavior can be different. Imagine that you are an operator of this reactor and you are operating it on a day-to-day basis. One day you change the flow rate by a small amount, and then you see the reactor performs completely differently. The conversion goes down. You have no idea what is happening, right? Until you understand the dynamics of this. As you change the parameters, what happens to the conversion? Conversion can drop to a significant value. So for these parameters, I can use the same setup. So my initial guess is, so it is the same problem I'm going to solve using the same set of parameters. I'm going to solve it 3 times, okay? But each time I'm going to give it a different guess. What would you expect in the previous case? Okay, here I had a guess of 0.2 and 380. If I give a different guess, what do you expect? It will converge to the same value, right? If there is a unique solution, no matter where you give your initial guess, it should converge to the same solution. But if you have multiple states, then depending on where you give your initial guess, it will go to the closest solution that it finds. Okay, so the very first case, I'm giving you. Take that out. Okay. An initial guess of 1.7 and 320. I'm going to run this. And I get a steady state solution of 1.78 and 331. Okay? And that will satisfy the equation because FSOL found those values. Right? The next time I'm giving it 1.3 and 350. Not significantly very different. 1.7 to 1.3 and 350. Exactly the same problem, same set of parameters. I haven't changed any parameters. I was expecting to go back to the same solution. And what happens is, let me set a breakpoint here and stop. And take that out and continue. So it is a different solution, 1.37 and 349. Okay? And this is the second solution for the same set of parameters. And I change it to 0.15. Conversion is now much lower. This is an initial guess closer to the lower conversion solution. Okay? And let me set up a breakpoint there and run that. And I get a third solution that is 0.15. So I have 3 solutions here, okay? 1.78, 1.37, 0.159. If you ask the question, is that all? The answer is we don't know. Okay, there may be other solutions, but by searching under different areas of the initial condition, I was able to get these three solutions. The more interesting question would be, will I be able to get all these in an experiment? If I'm running the plant, will I be able to see all these? And the answer to that turns out to be, you can never realize the middle one. Okay? That's because it is unstable. How do you know a solution is unstable? What do we mean by a solution is unstable? Pardon me? Eigenvalue, exactly. So if you know the linear analysis, then you know that if you linearize the equation around the steady state, and we will again show that later on when we are looking at the stability analysis, and calculate the eigenvalues of the linearized system, it says that the eigenvalue is positive, which means that the solution is going to blow up. So if all the eigenvalues are negative, in this case we'll have two eigenvalues because it's a 2 by 2 problem. If both the eigenvalues have negative real part, it will be stable. You will find that is the case in the first one and in the third one. The second one, you will find that one of the eigenvalues is positive. That means it's going to grow. And we will see the reason why that is. You must have seen it in linear algebra, but we will come back and review that as well. Okay? So typically this is what happens. When you have three different solutions, one of them turns out to be unstable and the other two are stable. And if you do the same trick as we did before, that is, this is now for a fixed flow rate of 1. Okay? So if you did this for flow rate of 2 and 3 and 4, that is, you need to put a loop around this for various flow rates of 1 to 30. And in each case, give a different initial guess and see whether you can find three solutions. What you will find is the structure actually looks something like this. Something like this, right? So you continue to increase and you will find that all of a sudden the solution jumps to a different state. And you continue increasing the flow rate, you'll find that you get a series of points like this. So in your forward sweep, all you will get is this part of the graph and then this part of the graph as you continuously increase the flow rate. Okay? And then you start with this one and go back, you'll be able to come back all the way here and then it will jump to this. You will never get the intermediate branch. Okay? And that branch is the one that is unstable. So to be able to get that, you need to use something called an arc length continuation method that we will also see when we look at the numerical methods. Okay? So this is typically what happens when you have a nonlinear system. Very complicated path of solutions as you change a parameter in the problem. In this case, it is the feed rate as the parameter in the problem. Am I making sense? Are you guys following me? If there are any questions, please do stop and ask. Yeah.
So, for example, if we are setting the temperature like in the middle value, we had like three values, and you said the first and third were like much
Stable.
stable, and the second one was not. If I'm setting the temperature and other parameters to the middle value, will I be getting anywhere close to the concentration that I'm expecting, or is it going to go up to the first or the third one?
Good question. So if what happens in a real experiment, I fix when I start up, my initial conditions to be close to somewhere here, right? In fact, as close as possible somewhere here, or in fact even on that. You adjust your temperature and concentration so that you are on that. Because it is unstable, you will find that it will just go away from there to one of the stable steady states. You can simulate that in a dynamical problem. That's the next thing that we are going to do. So all we are doing right now is you have a steady state. We threw the left-hand side ddt term. We have a steady state solution, and we solved it repeatedly, and we found that at a given flow rate, you can have three different solutions. That doesn't occur for all flow rates. It occurs only for a range of flow rates. If the flow rate is above that range, you'll get a unique solution, which is a high conversion one. Or if you have a low flow rate, you have a unique solution also. But in between, there is a range where you can have up to three solutions, the intermediate one being unstable. Now, this range of f over which you find multiple solutions itself will depend on other parameters. For example, if I change the cooling water rate, you might find I actually expand this range of multiple solutions. or I can shrink it. Okay, so that really gives rise to very fascinating solution behavior as we change the parameters, cooling water rate. And this is why we identified what are the controllable parameters in the problem. Okay, so all the ones that you see in yellow that are highlighted, the flow rate, the inlet concentration, inlet temperature, coolant flow rate, are all controllable parameters. So by controlling this, you can move the reactor to any one of the complicated multiple steady states.
So depending on my initial guess, I can move for a particular flow rate, the concentration to the lower value or the higher value. If I'm closer to the lower value in my initial guess, it's going to convert.
Okay, you are using the word initial guess. So we need to make a distinction between the steady state solution and the dynamical solution. For the steady state solution, these are indeed initial guesses. Okay, because it is a guess to an algorithm that uses trial and error method to find a solution. Okay, this has nothing to do with reality. So I can guess anything I want, but there is only one solution that it will go to. Okay, if I give a different guess, it may go to a different solution. But each attempt, the fsol is going to give me a converged solution that satisfies that equation, f equal to 0. Okay, but initial condition is different because the problem that we are solving when we are talking about initial condition is the full dynamical problem. Okay, so now we have the left-hand side, and our solution to the full dynamical problem is going to look something like this. Ca as a function of time and T as a function of time. Okay, so now I have an initial condition which is different from initial guess. Okay, an initial condition can be somewhere here and it just goes to a steady state. Initial condition can be here and it goes to a steady state. What fsol found for us is this value once it reaches steady state. Once it reaches steady state, you know that there is no gradient. The gradient is 0. Okay, so in fact you can say I can find the steady state solution without using fsol if I have an algorithm that will give me the entire curve for the dynamical problem. Right? So you need to understand the difference between the initial condition and an initial guess to fsol. Okay? These are called initial condition because they are specified at t equal to 0, and the solution to the dynamical problem that you see is the entire curve. What it means is if I take a point here and take the derivative dt, plug it into the left-hand side, and plug everything else to the right-hand side at that temperature and at that concentration, that equation will be satisfied. Okay? It will not be equal to 0. The dt, the derivative that you see here with respect to time will not be 0. Similarly, dc dt will not be 0. But I take that and put it in here and put it in there. And at those concentrations, the temperature I plug the right-hand side, left-hand side will be equal to the right-hand side. But only when the right-hand side is equal to 0, it means that the derivative is 0. Then I have found the steady state solution. Okay? So these are called the initial condition. So what does it mean if I give it a different initial condition? If there is only a unique steady state, the path may be different, but it eventually should go to the same thing. But if you have multiple states, depending on what your initial condition is, it may go to a different steady state. Okay? Is that clear? Okay? In fact, that's what we are going to see next. Okay, so we saw that there are 3 different solutions and we computed all of them. Now we are parked in line 57. Part 4 of this problem is find me the dynamic solution, the curve that I talked about, evolution with respect to time. Okay, so the tool that is available in MATLAB to do that is not fsol, but it's called ODE45. Okay, what does ODE45 do and how does it do, we will see later on. But I'm just showing you, if you are given a set of ordinary differential equations of the initial value type, what tool will you use and how will you use it to solve that problem. Okay, so this also has the options parameter, and you can specify the tolerance as the error, but you use it in the same way. Instead of fsol, you have ODE45. Control goes to a different algorithm. Okay, But now time is a variable. So you need to specify both time and the state. X is still a state vector. The state vector contains two elements in this case, Ca and T, concentration and temperature. Okay? So I wrote another function called CSTR dynamic, and that has time as one of the input, state, and then all the parameters, 15 values of the parameters. Okay? So that's how I tell ODE45, this is the problem that you need to solve. I'll show you how the problem looks. It's going to look exactly as the two equations that we saw. And then the next parameter is an initial condition, not an initial guess, right? This one simply says integrate in time from 0 to 10 seconds or minutes, whatever the units are. Okay? So that's called the range for a t. Over what time range do you want to integrate to plot the graph? Okay? And the next one is your initial condition. Okay? So xs is a value vector containing two numbers. Those are the initial conditions for the problem. And then the options passes that tolerance. Any questions on this? So what we are trying to do with ODE45 is construct these curves as a function of time, going from 0 and arbitrarily stopping at 10. You might find it's not enough. You may want to integrate it to 20 or 100.
So that is a trial and error process. When will my solution reach a steady state?
You don't know a priori.
That's a trial
Yeah.
and error process?
It is kind of trial and error process, because those that are kind of good in analytical work can look at the equation and estimate what the time constant for the problem is. That is, what is the order of magnitude, and that depends on all the parameters, the heat capacity, capacitance of the reactor, etc. For example, a quick measure would be if you know the volume of the reactor and if you know the volumetric flow rate. So how long does the fluid residence time, average residence time? So if you get an estimate, divide one by the other, volume divided by the volumetric flow rate will have the units of time. That simply says that over that time, you would have replaced all the contents in the reactor with a new feed. That's your average residence time. So take your time interval to be maybe 3 times the average residence time, 4 times the average residence time, right? That's an intelligent way of doing it instead of just guessing, trial and error. Any other questions? No? So this is the range of time, and this is the initial guess and options. Okay, so now what is going to happen when I continue to execute is control will go in line 58 to ODE45. ODE45 is a huge algorithm, but it is going to continuously talk to the CSTR dynamic and get back the function values and try to construct the solution and return the solution in this vector. So T would be a vector of time, and X would be not a two column vectors. The first column will be Ca, the second column will be temperature as a function of time, and you can plot those. Okay, so maybe we can stop there. I'll show you how does the dynamic CSTR dynamic function look like. So it's exactly the same function that I had before, okay, except I added T. Why? Because ODE45 expects the first parameter to be time. The problem is time dependent. So the first parameter is time. The second parameter is the state. In this case, a 2-dimensional state vector, concentration and temperature. The third one is the parameter. Okay? And let's forget about this for a moment. I'll come back and explain this. So these 4 lines are exactly the same lines we had in FSOL, for FSOL, right? So now you need to ask yourself, how can the same function, when fed to FSOL, finds the value of the function that is equal to 0, when fed to ODE45, helps in constructing the solution. Okay, so you need to understand the nature of the algorithm that does it, and it's not very difficult to understand it. So let me show you why that works. Okay, so now I'm plotting Ca as a function of time. Okay, so I'm trying to construct a solution that may go to a steady state like this. right? So if you give me an initial guess, if I take that initial condition, and I put it into those functions f1 and f2, what do I get? Not 0, because it's not steady state. I will get two numbers, right? f1 and f2 that are non-zero. Okay? But what is that f1? f1 is nothing but dCA dt equals f1, and dt equals f2. If you look carefully in the way that I have constructed this, here I have v on the left side, right? But I have taken this to the right side and divided everything by v, so that I have only dCA dt equals that function. Okay? And I've done the same thing in the second one. Now for the fsolve problem, it doesn't matter, because you can just multiply it out and throw it out to 0. But now for the dynamic problem, you must have the whole thing divided by rho VCP. Okay? Because the time constant information is contained in that, right? And you will see that I have it here. I also had it in the original function for fsolve because it didn't make any difference, but here it will make a difference. Okay? So why does it work? It works because once I've written it like that, if I plug in the value of that CA and T and all the parameters, I get a number. That number is the slope of the function at that point, at any point. Once I know the slope of the function, I'm taking an incremental step, a small delta t. If I know the slope here, I can predict what the next value will be for CA and T. That's the algorithm that it uses, a more sophisticated version of this concept. So at every point, when I send the value of CA and T, I get f1 and f2. They are the slopes of the function. And I can use that to project what the next value of CA and T will be and accumulate the whole vectors and construct that solution. Is that clear? Okay. So I really don't want to set up a breakpoint inside CSTR dynamic, but the communication will keep going back and forth. Would you like to see that as it runs? You guys are pretty good now, right, in understanding MATLAB. So if I hit continue, it's going to go to ODE45, solve the entire problem from time equals 0 to 10, get back the vectors, and be ready to plot the result. It's done. Okay. So if I look at T is 0.25, 0.5, 0.75, and you will see something very funny. How many elements are there? 113. They're not equally spaced. Do you notice that? Initially it was 0.25, 0.5, 0.75, 1, and then it started doing 1.005, 1.01, etc. So the delta T that it takes is dynamically changed. How does it change? What logic does it use to change that? Because we told it that the tolerance must be 10 to the minus 6, meaning the error in CA and T should be less than 10 to the 6. Okay, so it uses that. So it actually takes two steps, one with 0.25, another one with 0.125 maybe. So to go to the same point. So it has two estimates of the solution. And it compares the two. If this is less than 10 to the minus 6, it's acceptable. It'll go on. But if it is more than 10 to the minus 6, it says I'll back off and take two smaller steps. Okay, so it does the automatic step size procedure. And that's why the T would be a vector that is varying intervals. And X will be two columns. The first column is concentration, the second column is temperature at those times. Okay, now I can plot that. I don't know whether you guys are familiar with the subplot. Subplot essentially does two plots on the same page. And in the first plot, I'm saying plot the first column. Okay, that's going to be the concentration. And the second thing I'm saying, plot the second column of X, which is the temperature. And this one simply says there's going to be two graphs. Okay, and this is essentially using a matrix notation. You can put 4 there, that means it's going to be 4 graphs. And then here it says 1, 1 is the first element, and then 1, 2 would be the second element below that. 2, 1, then it will put it side by side. So it's like a matrix of figures that it constructs. So let's just step that. And where is the figure? Can you guess what's happening here? I didn't intend that, so I didn't explain that. This is the upper graph is the concentration, the lower graph is the temperature as a function of time going from 0 to 10. But if you go back and look carefully at what I specified as my initial condition, what did I specify that as? XS1 is here, right? It is the converged result for the first steady state. Right? I gave the converged result as the first steady state as the initial condition. Okay? And so the graph makes sense because things didn't change. It was already the steady state. Right? So it was going steady, constant for a while. But then it changed. Why did it change? Because I did something here, but I didn't save it. I wanted to comment it out and show you what happens. In fact, I've commented it out, but I didn't save it. How do I know I didn't save it?
Star.
You see the star there, right? So I will save it now and then go back. I don't know how to make it go to a run to cursor. Oh, okay. Is that possible? Let me try that. Nope, it didn't work. Let me take all these. Let me take this out and run one more time. No, it's producing the same graph. Something is really weird. Oh, it's not in the right place. This is in the folder lecture 04. Let me open the one. Okay. Yeah, this was not commented out. Save it. So I'm solving only the dynamic part. I'm solving only this section. Okay? So figure 1. So what do you expect? It was the steady state. I gave the steady state as my initial condition. So it didn't change, just stuck to the steady state. That shows that it is stable steady state. Okay? So if I start anywhere near it, it'll go to that. So if I perturb the steady state to some other value, instead of XS1, I say plus 0.2, for example. Then I'm perturbing the initial gas from steady state. So let me save this and run it again. And you see the initial state is perturbed, but it goes back to the steady state. So it's a stable steady state, the first one. The second figure shows the second steady state. Here I'm starting with XS2. That's a steady state that's supposed to be unstable, right? So I look at figure 2, oops. And can you explain this? What's happening in figure 2? This was the steady state for the second solution, right? So it is taking a long time, seems to be stable, but eventually it goes away and there is not enough time for it to reach a new steady state. If I had increased from 10 to 50, it would go to the second steady state. So there are two things that you need to understand in interpreting this. First one is, why did it take that long, 8 seconds or 9 seconds before it started drifting away from that? Because we are giving up to 10 significant digits the exact solution that was found from the steady state as the initial condition. and the growth of that instability is so small. The eigenvalue of the positive one is so small that e to the power lambda t is the one that allows it to grow, right? So it's taking a long time for it to move away, but it is unstable. If you give it sufficient time, it will move away. Okay, so it's moving to the different steady state. Now, if you look at the third figure, what is this one? Third supposed to be stable, right? Is that significant? These oscillations, do you think, are they wild? What you need to look at is the scale on this thing. Solve point 1597, 1597, 1597, right? So up to 5 significant digits, it's the same result. We are asking for the solution only for 6 significant digits. So there are errors in the solution that are propping up. And that's why it seems completely random, because these are coming from round off errors. Okay? So what you see here is essentially the error in the solution because we have truncated. We have asked for solution only up to 10 to the minus 6. If you ask for 10 to the minus 10, it will remain as a stable steady state solution. Okay? So this is the simulation for the dynamical problem where we haven't done anything to the input. We just gave the initial condition and saw what happened. So for the first and the third one, it remains stable. For the second one, it moves away. Now we can activate that perturbation, and in that process you also see how to enforce control actions and comment. Okay? So what does that piece of code do? Remember, the control comes from ODE45, the integration routine, to this function, which is the problem that we are trying to solve. So it's exactly the same as before in terms of parameters, but it will come within this function with the value of t. What is the current value of time? Because it needs to estimate all the function values, the current value of time. So time will be available. And then I'm saying here, if t is greater than 1 and t is less than 2, t0 is 353, else t0 is 343. Now what was t0? t0 was parameter 4, and parameter 4 was 343. Okay? I'm maintaining the inlet temperature at 343, but I'm introducing a control action. Remember, I identified 4 variables as control variables. I'm introducing a control action when the time is greater than 1. That is, between t of 1 and 2, I'm perturbing the system. I'm increasing the temperature from 343 to 353, and then after 2 seconds, I'm bringing it back to 343. Do you understand what's happening in line 19 to 23? Yeah? So I'm just perturbing the system and bringing it back to see whether each one of the steady states is going to go back after responding to the perturbation, or is it going to go away from somewhere else. Okay? So let me save this file, and then go back to the script and run the script one more time. Now explain the 3 figures. There is your figure 1. Oh, I should have done something wrong. What did I want to
You had perturbed already.
Right. Very good. I didn't want to perturb it, but I had saved the perturbed version. So what I'm doing is, in each case, I'm giving the previously converged steady state as my initial condition, and then integrating. But I'm perturbing the solutions at between t of 1 and 2. And I want to see whether it will come back to the same solution or go to the different solution. Okay, so now let me run this. Okay. So this is 1, the first steady state. Okay, so it is remaining steady state. At t equal to 1, I perturbed it. So it responds to the perturbation, but it takes a longer time. Even though I turned it back to the normal at t equal to 2, the dynamics of it is such that it takes longer to come back to the steady state. But it goes back to the same steady state as before. That's another way of finding the stability. So if you have a stable solution, you perturb it, it goes back to the same thing, you know that it is stable. Eigenvalue will give that mathematically. This will give you by intuitive testing in the lab. So same thing for the temperature. It's perturbed and then it goes back to the same thing. In figure 3, which is the third steady state, it's also stable, same thing happens. At 1 I perturb it, it has undershoot, overshoot, etc., but it goes back to the same steady state. Okay? But figure 2 is for the intermediate solution, which is unstable. That instability took about 10 seconds for it to slowly grow without any perturbation. But when I put a large perturbation between 1 and 2 seconds, you see that it switches immediately to the which solution? The third solution. Okay? Because it's closer to the third solution. And the temperature also does the same thing. So in terms of concept, we are covering a lot of things. I don't know how many of you are completely familiar with dynamical systems and the complex behavior they can exhibit. But here is a problem that's very rich in terms of multiple steady states, their stability. Things can get even more complicated in the sense, for these ordinary differential equations, there need not be a steady state at all. Even though the forcing is steady, everything is operated under constant condition, the response can be sustained oscillations. And those are called limit cycles. In reactor system, you have it. Of course, in human body, you have it. If you look at the heart pumping, it's a very rhythmic, periodic behavior, right? And so solar systems are examples of the motions of orbits or periodic systems as well. So there are a lot of examples where a system of dynamical equations, ordinary differential equations, subject to constant forcing, can give rise to periodic oscillations. In fact, in fluid mechanics, it is thought that is the origin of turbulence. The flow, in laminar flow in a pipe, becomes unstable, gives rise to these oscillating flows, eventually introducing all kinds of frequencies, giving rise to fully turbulent flow. Okay? And that is one route to what is called chaos. There are nice popular books on chaotic dynamics that explore these concepts of dynamical systems. So we will see examples of those later on. Any questions on that? Okay. I think that's all I wanted to show on this problem using MATLAB. So what do we know so far from MATLAB? How to solve a system of linear equations, no matter how big it is. We have done 10,000 by 10,000 equations using backslash operator and CGS, the iterative method. We know how to solve a system of nonlinear algebraic equations. We've done it for 1, for 2. If you can do it for 2, you can do it for 20 or 20,000. FSOLVE is the tool. How it does it, we will see later on. Then we have seen ODE 4.5, a tool that solves ordinary differential equations. Okay. And for that, you need an initial condition. For FSOLVE, you need an initial guess. But we've seen in the process that these nonlinear equations can have multiple states, and so one has to be careful in interpreting the results. So no questions. I'm going to close this and go and show the same thing in COMSOL. How do we do this in COMSOL? Let me open up 2 text files. I'm preparing this file for COMSOL. Can you kind of guess what it is? Just the parameter values. This is how COMSOL expects it. Put a symbol next with a space, put its value and a space, within quotation mark, some comments that you want to put. So there are 15 values here. Okay? And then I have another file that has the 2 equations. These are the same equations that we put in MATLAB into that function, CSTR FN and CSTR dynamic, right? So 2 lines, but again, it's the same format. The first one is the symbol. The next set of strings is the equation itself. In terms of all the symbols that we have introduced in the other table, okay, we're going to import both of them. You can enter one by one, but it's time consuming in a class, so I just saved it here, and I will show you how you would import that. Okay, and you will notice that in the first equation I don't put them in quotation mark, and then I have, of course, an initial guess and then some comments. In the second one I put them in quotation marks. Can you kind of guess why this is? I'm also guessing. I didn't read the manual, but I just saved it from COMSOL, and this is what it did. It put a quotation mark in the second equation.
It feeds it as a symbolic equation to the.
In both cases, it just treats it as a text of strings. Okay, but the way that COMSOL treats it is a space is a delimiter. Between CA and the next character that you see, the left parenthesis, I have a space. That means the next field is starting. And if there are no spaces after that, the whole thing is a string that goes into the equation. But in here, I have one space that's hanging around freely. Why did that happen? Because I just copied and pasted from MATLAB function into this. And in MATLAB function, I had them on 2 lines. Okay, so I had to put them one after the other. So I accidentally ended up putting a space. So to tell that it is all belonging to the same thing, it puts a quotation mark at the beginning and at the end. And then you have, of course, an initial guess for that, and the rest are. You will see how they are filled in. So this is one way of writing or copying information from MATLAB to COMSOL, etc. Okay, to import information. But if you are patient enough, if you want to type the equations, you can do that as well in COMSOL. Okay, so so let me just open up COMSOL. So this is a file that I have saved. So I have already formulated the problem before and saved the file. COMSOL saves the file as, just like MATLAB saves the file as .m file, COMSOL saves it as .mph file. Okay, so when you click on it, it automatically is associated with COMSOL, and it opens COMSOL and reads the entire problem. Okay, so all these folders I have assembled just before coming to the class to kind of speed up things. Okay, so what I want to show here is these definitions. Okay, so you see all the variables that have been defined, and you can read them by opening this file. Load from a file, it will read the data from that file and populate it with the data. Or after you enter it manually, you can save it so that next time you start, you can read it as well. Okay, so these are the 15 parameters. They are defined under definitions. So these symbols can be used anywhere in COMSOL that you need them. Okay, and the next folder contains the global equations, and you see the equations there. So this was also written by hand by me into this and then saved it in the text file. Okay, so to save it, you either use this icon or to load it from here. So there are 2 variables, and the equation, if you want to see fully, you just select that and you'll see the equation in complete form. Okay, and similarly the second equation. Okay, and then the initial guesses, and you can put any description you want here, mass balance, energy balance, or whatever. Okay, we didn't put anything here. And that's it. So in COMSOL, if you recall, when you're starting this up, you need to identify this problem as a 0 dimension that tells it that it's an algebraic equation or an ordinary differential equation of the initial value type. Currently, it is algebraic equation. Okay, and the study you can specify as stationary or dynamic. Once you select dynamic, the same set of equations will be used with an initial condition to construct the entire trajectory of composition and temperature as a function of time. Okay, but right now it is solving as a steady state problem. Okay, so go to study and then right click and compute, and it solves the problem for you. And here is your concentration and temperature. Okay, now there is any questions on that? So when you are doing a problem in your next assignment, I will give you one to use both COMSOL and MATLAB. What you will find is the need to know. Okay, that comes only with spending time with COMSOL. Which folders have what parameters? How do you control that, right? So with a little bit of experience and exploration, you will find that the variables are defined here. Now I want to show how the continuation works in COMSOL, because as I said, that's a powerful method, and we will extend it to be even more powerful than what is built in here. Okay, so I actually forget, but let me see whether I can define variables, functions, probes. There is a place where you put parameters. There are parameters. You go to global definitions and identified parameter as P, and you give it a name. In this case, I'm going to put F, because this is now a distinguished parameter, meaning there is one parameter I want to change continuously and solve the problem repeatedly. In MATLAB, we write our loop ourselves, but here you don't have to do that, but you need to identify which is the parameter that you're going to change and what is its value. Okay, 1, for example, 30. Syntax error. Why is that?
I think value has to be on third one.
You think so? It makes sense, but it doesn't accept anything there. Let me see. Maybe just name and expression are the same, so I'll just put F there. Circular variable dependency detected.
What if it's F plus 1? Changing it back 1, right?
F is 1.
It is incremented.
Yeah, F is 1. Initial value of the parameter is 1. It accepts that, right? That's a parameter, which is different from the variables that we have here. So I need to remove F from the variable list, because F can be defined only in one place. Otherwise, it will pick this value and keep it as constant. So I right click on this and delete it. So I have only 14 variables with constant value and one parameter which is going to have a variable value starting with an initial value of 1. Okay. Then I go to study and I right click, and here I have a parameter sweep. Once again, I'm focusing your attention on the features that I'm trying to illustrate. But when you right click on this, there are 20 other different items, right? I don't know what they are. We will learn as we go along. Okay. So in this case, I just want to show you how to do the parametric sweep. So I select that, and it adds a parametric sweep as a folder under study. Okay. And now I need to identify which parameter I want to. All combinations. It should automatically show me. Oh, here, add. Okay. So when I add which parameter I want to continue, it shows that F is the only parameter I define. If you define F and T0 as two parameters in which you want to continue, it will show you two optional values that you can enter. Right now, F is the only one. So I add it, and here is a pull-down menu, but there is only one value. If I added another variable to the parameter list, that will appear as well. Here is the value list. Here I can use that syntax, MATLAB syntax, 1:1:30, for example. Internal parser error, okay, it doesn't accept that either. Range, okay. So it has a function called range, and it gives you a box, and you say 1:1:30. I think MATLAB also has a function called range with this syntax, but I thought in the previous versions it used to work. 1:1:30 would be interpreted because it's a MATLAB syntax. It probably will work. Another feature I should point out, COMSOL, when you're starting it up in the next room, will have several things. One is Classroom License Kit, which is what we are starting. The other one is COMSOL with MATLAB. So when you start that, it has the ability to communicate with MATLAB and use MATLAB expressions and functions. I did not do that. That's why I think it's not allowing me to use that 1:, context. Okay, so now, do you follow what I've done so far? Kind of struggled a bit, but I've identified one of the parameter that I wanted to continue, removed it from the variable list, and then identified the range over which I want to solve. So now I compute. Right click on that and say compute. So it would have solved for all of those 30 values, but I need to find out how to extract them. Data set, thank you. Tables. I hope it solved it. Output while solving. Okay. Plot. I'm not sure what it's going to do, but I'm going to click that and see what it does. Compute. Previous one?
Because I remember the last class you did that, you delete that previous result.
Completely? It's not allowing me to delete that. I'm afraid maybe it's... The range?
That expression, where we kept one, what if we try to write range in the expression?
Yeah.
No, in the
This parameter, the global definition.
Yeah.
There in the expression, let's try to write range.
Oh. I think that will work. 1:1:30. Yeah, here it's just an initial value, I think. This is what I remember. And it did accept here, right? It should plot it. Oh, convergence plot. Oh, there it is. So this is showing, what is it showing? It's a convergence. For every value of f, It starts with the large error and then goes down to 10 to the minus 4. So this shows f equal to 1, 2, 3, 4, etc.
So where it ends is the steady state.
Yeah, it's converged. We are solving only for the steady state right now because the problem is stationary solver, right?
Now the issue is which way is forward, which way is back.
No, what this curve shows you is the convergence plot, meaning how does the error go down with iteration number. So the first curve is for f equal to 1. The error for the initial guess that you give was large, and it is driven down to 0. To solve the first problem. Then it goes back through the loop and sets f equal to 2. The error is large. It will automatically take the previously converged result as the initial guess. Okay, and then it drives that. So it's like fsolve driving the solution to 0. COMSOL does the same thing. So each of these curves is for different values of f. Okay? And it has solved 30 times, and in each case it has brought the results down to 10 to the minus 4. So it has solved 30 times. I know that from this graph. But the question is, where is it saving the result so that I can plot it? It must be in results in data sets.
So in the tables it's showing table 1 and table 2.
Yeah, but they both show the same thing. Table 1 and table 2 doesn't have anything. Oh, okay. Update. Settings, full precision, scientific notation. Global evaluations. I'm sorry, I shouldn't be wasting this time. I should have figured this out before. Anybody has any ideas where it is saved?
Maybe just the result, you just delete the previous one. Because I remember last class, we solved different problem, we delete the previous one.
Right, but I don't know how to delete it because it doesn't give me the option. If I right click it, it doesn't allow me to delete.
Maybe delete the data sets, the table and the derived values. Yeah, I think that's how.
Evaluate all. I don't have a delete option here too. There. I don't know what I did, but thank you for pointing me in the right direction. All I did here was evaluate all, right? And then it shows me a table with 3 columns, and these are the flow rates and the concentration and temperature. And I think you can now plot this. Yeah, another one that indicator is this log because it shows you as it solves f equal to 30, f equal to 29, how many iterations it took and what are the errors, right? So that also is an indication that the continuation method has worked. There is a way to make this plot, but I'm not sure I can figure this out now.
Maybe you need to create the plot first.
You need to create a plot, yeah, 1D plot group. Plot. Plot
And then
what?
right-click the plots. Right-click the plot branch. Oh, you have to create the line plots.
Create what?
Line plot on top.
Oh, on the top.
that line graph.
On top.
Yeah.
The notification bar on top.
There's an option called line graph.
On the toolbar.
Line graph.
Yeah, sorry.
I see. Oh, I see. That will add. But it is already added
Select
that
it. Yeah, you can select it.
from parent. Line graph. X-axis data. I have no idea what I'm doing now. I better stop at this point. It is possible to plot this, okay, one against the other. And what you will find in this case is for the parameters that we have chosen, it is a smooth curve because there's only one solution. But when you change the parameters to the state where you have multiple states, the graph will look something like this. When you're plotting CA versus F, you'll find a graph like this, and then it just jumps. That's all you will see. Since you don't see even curves, you'll see these points. Each one for different values of F. Okay, and same thing will happen for temperature as F. So when you see something like this, you need to be able to interpret that something funny is happening here between this flow rate and that flow rate. And if you go and see where the log is, you'll find that the number of iterations that it took typically is of the order of 3 iterations. But when it switches, it'll need more iteration because this is a poor initial guess for this solution. But there is no solution beyond this because the curve actually comes back and does this, right? Something like this, right? So that will be the full nature of the curve. But in this simulation, this is what we will see, only a partial picture of it, okay? Now, how do I solve a dynamical problem for this? I need to, I guess, close this, and when you're restarting it, you need to pick the right physics model, okay? So I'll just show that part, which physics, and then maybe the next class we'll try to continue to do the dynamical part in COMSOL. And then the only model that we need to do is a boundary value problem, how to solve this in MATLAB and in COMSOL. Okay, so a model wizard, pick 0D, okay, and then pick, I think that's it, done. And you need to add a study which will be not stationary but time dependent. That enables something equivalent to ODE 4.5 in MATLAB, solves the ordinary differential equation of the initial value. Okay, so the study is now time dependent. And of course you need to now import all the parameters and the variables, etc. So if you go here, definitions, variables, and then you can just open this par and define all those variables, okay? And then go to equations, add physics, global ODE and DAE, add that, equation view, and you can open the equation text and you import all the equations. It's the same equation as we saw in MATLAB. The same CSTR function is passed to FSOLVE and to ODE 4.5. They interpret it to give you different solutions. One is steady state, the other one is a dynamical one. Same thing here. So these are the same equations, same parameters, except the solver is now a dynamic one instead of a steady state one. Right? So this is time dependent. Okay, so it adds the dCA dt term. That's why it's important to take anything else to the right hand side. If there is a factor multiplying dCA dt, you need to take it to the right hand side. Because MATLAB, COMSOL, all it does is it's adds dca dt to the left-hand side, dt with respect to time on the left-hand side of the second equation. And then it uses the appropriate algorithm, something like ODE 4.5. And we'll see the details of the algorithm later on. Okay? And then I think you just need to compute. So what do you see? You see both the graphs, unfortunately, plotted on the same axis. Right? So this solution is, the lower one is the concentration, the higher one is the temperature. But we gave the initial condition as the steady state solution itself. That's why it's just flat. If you gave anything else, it will change to the steady state. Okay. So fairly easy to use in COMSOL. It requires very little programming. So people that hate programming will find COMSOL to be an easier one, particularly as you go into solving boundary value problems and partial differential equations, because we're going to be doing the same thing, defining the problem by just picking the right tools for assembling the physics, for assembling the equation solver, and then interrogating the results. So the same framework works for a whole class of models that we can see later on. Okay? So I think we'll stop there and continue on Wednesday with the next model.